Hi, I'm Oliver Schön, and today I'm presenting our paper about multi-objective physics-guided recurrent neural networks. My co-authors are Ricardo Goethe and Julia Timmermann. In the beginning, I just want to say a few words about myself. I'm currently a PhD student in computer science at Newcastle University in the UK, and I'm working on formal methods for cyber-physical systems. Last year, I was with the Heinz Nixdorf Institute in Paderborn, Germany, and working on hybrid modeling. This also resulted in the paper, which I'm presenting today. For the agenda, it's going to be very straightforward. We're going to start with the problem statement. Then I'm going to introduce the approach that we pursued, and we're going to talk about some findings and conclusions. So consider a black box system, which has a system state X, a control input U, and can be described by a deterministic function F. We now want to find a model for this system. At this point, we also acknowledge that the laws of physics shape the way this system behaves. Therefore, we also indicate this as an additional input. One traditional way of modeling such systems is what we call physics-based modeling. We're starting from the fundamental laws of physics and derive models from a theoretical standpoint. One downside of this is that for complex systems, this can become very costly. We have to capture all the nonlinearities. We have to identify several parameters. And in some cases, we sheer lack the system understanding to do it. Therefore, engineers nowadays often resort to data-driven alternatives. But for these, we have the problem that we cannot train accurate models that extrapolate well on very little data. One cause for this is also that we don't respect any fundamental laws of physics, which we will refer to as physical plausibility. The problem with this is, except of those extrapolative impairments, of course, that in the case of anomalies, we cannot say whether they are exhibited by the actual system that we're capturing or they stem from the model. In other words, the results from the data-driven models that we got are not traceable. It's not possible to use any common analysis tools like for stability. And as a scientist, this also means that we can't get any sound conclusions from the obtained models. Therefore, we try to find some modeling method that combines the advantages of the two approaches and at the same time also tries to alleviate their shortcomings. So in summary, our objectives are to reduce the modeling effort by utilizing data-driven methods, in our case for non-autonomous time-continuous systems. The second one, to improve model accuracy by starting from a purely physics-based model and then somewhat shaping the dynamics to calibrate it to the data. This is also referred to as physics-guided modeling and results in hybrid models. And the third point is that we want to maintain some physical plausibility. Though we don't give any guarantees of physical correctness, we want to incentivize this. Note that we therefore make use of existing system-specific, but also general scientific knowledge. I now want to introduce the approach that we pursued here. This approach has two stages. For the first one, we quest to merge data-driven and physics-based models. In the literature, this goes back to physics-guided modeling, as I said before. And one of the original papers on this was by Karpathy et al. In 2017, where they merged ordinary differential equations, ODEs, with neural networks. And that's how they got PGNNs, physics-guided neural networks. This was later extended by several authors, for example, by Jia et al., using also recurrent neural networks. That's also what we're doing here. We're pairing a physics-based models, which is defined by some ordinary differential equations, with a recurrent neural network. This has the advantage that we're able to capture long-term relations in the data as well. Like the other authors before observed, we're hoping for synergetic effects, like reduced data requirements, but also increased model accuracy and the like. To clarify the notation here, H stands for history and is basically just the sequence of timestamps, states, and inputs. So as you can see here, we have a physics-based model, which is a system of ODEs, and serves as an additional input to the recurrent neural network, which now has not only the state evolution and the input evolution next to the timestamps as well, but also the output of this physics-based model. And we try to now learn an even more accurate model by doing this. The second part of our overall approach is a multi-objective strategy, because what we want to have is not only to train models that are not only accurate, but also respect certain laws of physics. You can come up with some wild ideas here, but what we do is here that whilst training, we not only optimize for the error on the training data, but also on some physics-based losses. And this is based upon vector performance index optimization introduced by Kreisel, and Steinhauser all the way back to 1979. And I just want to say a few words about this now. They're defining a training objective J, which now becomes for us the network's loss function. And we search to minimize this objective in every training iteration I. The way this objective is defined is that we have non-negative loss terms. And for each, we have a normalization factor C, which is also referred to as a default value. What we now do can be seen on the right-hand side, that we gradually contract those boundaries, those default values, and get from some point which is defined by the losses in iteration I to some point which is defined by the losses in iteration I+1. At some point, we arrive at some Pareto optimal point if we always contract those boundaries. So every iteration just contains optimizing the objectives, retracting the boundaries, repeating. This is what we call a multi-objective physics-guided recurrent neural network, because we pair the physics-guided recurrent neural network as before with this new multi-objective loss function. In our case, we now use two loss terms. On one hand, the normal error on the training data, but then also an energy term. And this energy term is just an energy balance of the system. And what we do is we penalize non-energy conserving models. We therefore incentivize physical plausibility of the networks that we observe. I kindly refer to our paper for further information on this if you're interested. Because I also want to spend some time now on showing some experimental results. To test the performance of the new approach, we carried out some simulative and one real data case study. Today, I'm just going to show the results for the latter case study because I think it's more interesting. So in particular, we're looking at a real data from our lab-owned test bench for machine learning methods, which is a golf playing robot that you can see on the right-hand side. We also have an approximated dynamics model, which you can see on the left. This model is the merit of one of our master's students, and it was the result of extensive modeling efforts and parameter optimization. This model now has a system state, which is defined by the angular velocity and the angle of the beater. So in our case, this approximate model now becomes the physics-based model in the PG-RNN case, which is shown in the yellow square. What we now do is we utilize the data that we got from our system to train the RNN part and get a more accurate model. The general setup for this is that we train and test 16 networks each, and we then calculate the average error and standard deviation over all of them. For all the models that we consider, we also vary the amount of training data to see what impact this has. So now I want to show some results. On the right-hand figure, you can see eSim, which is the simulation error. This is basically just a performance measure for the accuracy of a model when it's simulated. Here we display for all the models that we considered the mean and double standard deviation over 16 networks, as mentioned before. And also in red, we note the baseline, which is the physics-based model that we used in the PGRNN and the MOPGRNN. So let's now look at the RNN, which is just a data-driven RNN, just utilizing the data from the system. And we can see that the error remains way above the one of the physics-based model, so way above the baseline. We also can see that we have a big influence of the training data amount. We need at least 9 training samples to get near to its performance. For the PGRNN and the MOPGRNN, which are based on the MFE, we see pretty much on par results, with the MOPGRNN having slightly lower error rates and also more consistent results. Between the lines, we also saw faster convergence and improved trainability. Now, a part of these improvements on model accuracy, the MOPGRNN also is supposed to maintain some level of physical plausibility. And I want to emphasize this by the next plot. What we see here is the energy balance for the system and the MOPGRNN. So we basically took for this figure one trajectory of the actual system, and we simulate the MOPGRNN just using the initial point and the control input. And the deviation between them is now the red line. This is exactly what we should look at. And what we can see here is that it stays very low for short horizons like 10 seconds or 20 seconds. This might be even a very long horizon if you have use cases like model predictive controller where you have a feedback loop. So what we can take from this is that the MOPGRNN also maintains some level of physical plausibility, in addition to also having a lower level of accuracy, a higher level of accuracy. To summarize this, for the purely data-driven RNN, we saw unsatisfying results. We weren't able to get nearly the same performance as for the physics-based model, but for the MOPGRNN, on the PGRNN, we were able to improve upon it. For the MOPGRNN in specific, we saw more consistent improvements, and we were also able to maintain some level of physical plausibility for short-term horizons. This is where I want to end with today's presentation. I want to thank you for your attention, and also the organizers for giving us the opportunity to present our work here today. If you're interested, please check out our work. Thank you.